topic is on solving vehicle equipment specification problems with ASP. And there are a couple of co-authors from Japan and Germany. Okay. Terrific. Go ahead.
I'm Takeuchi. We talk about solving vehicle equipment specification problems with answer set programming. Vehicle equipment specification is the combination of vehicle models and equipment in automobile catalogs. The task of finding such combinations depends on various factors, including laws and regulations of countries or regions, market characteristics, dependency between equipments, customer preferences, competitors, costs, and many others. A great deal of efforts by experienced engineers has been made. However, the task has become increasingly hard because of recent globalization of automobile industry. We tackle mono and multi-objective vehicle equipment specification problems called CAFE problems. CAFE problems are vehicle equipment specification problems based on CAFE standard as a fuel economy regulation. The vehicle equipment specification problem is generally defined as the task of finding combinations of equipment types and equipment options for each vehicle model subject to a given set of constraints on variability, dependency, and fuel economy. The objective of the problem is to find feasible solutions, maximizing the expected sales volume. The CAFE standard has been adopted in the United States and the European Union and was recently introduced in Japan. The CAFE problems are real-world applications in automobile industry. This is an input CAFE problem instance. The example is expressed in OVN format. This triangle node represents equipment type, and this rectangle node represents equipment options. For example, this type transmission has 6 options: 680, 1080, HV, and so on. The example has 6 equipment types and 19 equipment options. Each type can select exact one option. It is variability constraints. It has 5 dependency constraints represented by arrows. For example, this LX requires 1080 and 18-inch tire. All types are mandatory types except sunroof. The value of options, the value of each option indicates the inertial working rating, IWR, which intuitively corresponds to its weight. For example, 1080 option, IWR of 1080 is 125. The number of vehicle models and 2 curves is given as input. For each model G, the IWR value of G is sum of IWR values of options implemented for G. The fuel economy of G, FEG in short, can be obtained from the IWR value of G through a correlation curve. In the same way, the expected sales volume of G, SVG, can be obtained through a distribution curve. Fuel economy regulations have been tightened in many countries due to recent international movement against global warming. The CAFE standard requires each automaker to achieve a target for the sales-weighted fuel economy of its entire automobile fleet in each model year. The following CAFE standard must be satisfied. The left hand, sales-weighted fuel economy must be greater than or equal to the CAFE standard value T. The value T is given as input. This is an example of optimal solution when the number of models is n equal to 3, and the CAFE standard value is T equal 8.5 km per liter. For example, vehicle model 1 has standard 4 grade, 2WD for drive type, V6 engine, 16-inch for tire, 680 for transmission, and no sunroof. Sum of IWR values of model 1 is 1,130, and fuel economy is 8.8 km per liter. Expected sales volume is 2007. Fuel economy and expected sales volume is obtained from sum of IWR values and two curves. Although the vehicle model 3 does not meet the criterion, the overall solution satisfies the CAFE standard. Answer set programming is a declarative programming paradigm, combining a rich modeling language with high-performance solving capacities. SP is well suited for modeling combinatorial optimization problems and has been successfully applied in diverse areas of AI, such as product configuration, robotics, systems biology, timetabling, and many more. Moreover, recent advances in ASP open up promising direction to make it more applicable to real-world problems, such as preference handling, constraint ASP, temporal ASP, multi-shot ASP solving, and many others. Such advances encourage researchers and practitioners to use ASP for solving practical applications. We propose the ASP CAFE approach to solving mono and multi-objective CAFE problems based on ASP. And we show that ASP technology allows to scale to real-world instances provided by a collaborating Japanese automaker. This is the architecture of ASP CAFE system. ASP CAFE reads a CAFE instance in the OVN format and convert it into ASP facts. These facts are combined with an ASP encoding for CAFE solving, which can subsequently be solved by off-the-shelf ASP systems, in our case, Pringo and Aspiri. For mono-objective CAFE problems, we developed two ASP encodings. The basic encoding can concisely represent the constraints of the CAFE problem by using only 17 ASP rules. The optimized encoding can reduce the number of rules after grounding because it strictly calculates the upper and lower bounds of the sum of IWR values. It can be more effective on large problems than the basic one. Multi-objective cafe problems involve multiple objective functions that are considered separately and optimized simultaneously. The extended encoding is an extension of optimized encoding to find the Pareto frontal. That is the set of Pareto optimal solutions. This extension can be easily done by utilizing the aspirin system on enhancement on Klingo with preference handling. This is ASP fact format of a cafe instance. The atom VP def represent the equipment type, and the atom VDEF represent the equipment options. For example, this atom VDEF 1080 transmission 125 represents that option 1080 is one option of transmission type, and its IWR value is 125. In basic encoding, variability constraints is represented by these rules. The atom VPG represents that the vehicle model G implements the equipment type VP. This rule introduces the atom VPG as a solution candidate for each model G and each type VP. In the rule 2, the atom VG represents that the model G implements the option V. This rule enforces that the model G implements exact one option V of type VP if VPG holds. Fuel economy constraints are represented by these rules. In rule 5, the atom IWSG represents that S is the sum of IWR values of options implemented for the model G. In rule 6, the atom FEG represents that the fuel economy of G is Fe, which is obtained from the IWR value S of G through a correlation curve, Fe map SFE. In rule 8, the fuel economy constraint is transformed into this form and is then represented in ASP's weighted cardinality constraints. The rule 9 defines the objective function of maximizing the expected sales value. The problem issue of basic encoding is that the rule 5 is very expensive for grounding and solving. The domain of S is quite naive. Again, S is sum of IWR, the sum of IWR of option implemented by model G. The lower bound means no option, and the upper bound means the total sum of IWR values of all possible options. This issue can be resolved by considering for each type I the minimum and maximum IWR values of options, which I can select, whether I is mandatory type or not. The domain, this is an improved domain. The lower bound is sum of minimum IWR values of options for mandatory types, and the upper bound is the sum of maximum IWR values of options for all types. The optimized encoding generates the atom IWRSG based on the improved domain. The optimized encoding is obtained from the basic encoding by replacing the rule 5 with the following code. We omit the detailed explanation here. For mono-objective cafe problems, we carry out experiments on 3 benchmark instances based on real data provided by a collaborating Japanese automaker. For example, medium instance has 186 types, 2026 options, and 147 dependency constraints. Our empirical analysis considers all combinations, 15 in total, of 3 instances and 5 different cafe standard values T. The value T range from 8.5 to 10.5. The number of vehicle models is n equal to 3. We use ASP system Klingo version 5.5.2. Time limit is 3 hours for each. This table shows comparison of basic and optimized encodings. The first column indicates instance name. The second column indicates cafe standard value T. Third and fourth column indicates expected sales volume of basic encoding and optimized encoding. For each combination, the beta bounds are highlighted in red. Asterisk indicates the value is optimal. The optimized encoding was able to produce much better bounds for all combinations of the big instance than the basic encoding. We here extend the ASP cafe encoding to find the Pareto front. That is, the set of Pareto optimal solutions of 2 objective cafe problems. One criterion is the maximization of the expected sales volume. The other is the minimization of the number of equipment options. The latter aims at reducing the number of production lines, as well as promoting mass production. This extension can be easily done by utilizing the aspirin's preference statement. The aspirin's preference statement is this form, where S is the preference name, T is the preference type, and EI is the preference element. In extended encoding, objective function is represented by these rules. In the rule A, the preference max SV aims at maximizing the expected sales volume. In rule B, the preference min OP aims at minimizing the number of equipment options. In the rule C, these 2 preferences are combined as all, according to the Pareto type. In the rule D, the combined preference all is declared subject to optimization. This table shows an example of Pareto frontal when the number of vehicle model is n equal to 3, and the cafe standard value is T equal 8.5 km per liter. The Pareto front consists of 4 Pareto optimal solutions. solution 1, solution 2, solution 3, and solution 4. They are not domained by each other. The expected sales volume decreases from left to right. In contrast, the number of options increases from right to left. The extended encoding succeeds in well-balanced solutions like solution 2 or solution 3, which are not obtained by lexicographic optimization. This table shows benchmark results of finding Pareto optimal solutions. The first column indicates instance name. The second column indicates cafe standard value. The third column indicates the number of feasible solutions. Fourth column indicates the number of Pareto optimal solutions. Last column indicates CPU time. For example, for small instance of t equal 8.5, we found Pareto front. Asterisk indicates the value is Pareto front. The extended encoding was able to find the Pareto front of all combinations of the small instance and cafe standard values. On the other hand, we met the difficulty of finding Pareto optimal solutions for both medium and big instances. We presented an ASP-based approach to solving mono and multi-objective cafe problems. Our proposal, ASP Cafe, is available from GitHub. For future work, our declarative approach can be extended to a wide range of regulations and constraints, such as multi-objective cafe solving, considering minimal perturbation problems, and the zero-emission vehicle regulation. Thank you for listening.
Thank you very much. Are there questions? My question is, do these car manufacturers, did they solve this problem also before your application? And if so, what did they use?
What do you mean?
So this problem has been there for some time. Has it been solved in a different way? Or is it the first solution that you present? Yeah.
Sorry.
This problem. Okay, I'm co-author of this research, and the problem was provided collaborating Japanese car maker, and it's in my knowledge, this is the first time to solve by ASP, and similar problem like product configuration for automobile have been solved ASP, but the aim of different. Basically, most of work is focusing on the detect inconsistency between the customer's preference and some car maker side requirements. But yes, maybe this is the original problem.
Thank you very much, because I believe that you could probably also use techniques like mixed integer,
Yes, we can use that.
linear programming, and I just wondered whether it has been done before.
I'm not sure
I'm not sure, but the MIP can be also used for this kind of problem. And I'm not sure the MIP solver, the support multi-objective optimization. I'm not sure that.
Neither am I. Uh, yeah, thank you. The other, are there other questions? All right. Yeah.
Thank you for your talk. Can your method find the true Pareto front? I mean the set of all optimal. I mean the true optimal solution.
Could you say again?
Can your method find true Pareto front?
To Pareto.
The optimal solution.
I suppose this is what the asterisk indicates, right? That this, you really could compute the entire Pareto front.
Pareto.
Yes. Yes. My other question was when you introduced the benchmark problems, right? It was curious to see that the biggest one had no constraints, right? But is there a reason for this? This seems unrealistic somehow. Can you go to slide 8?
This benchmark.
This one, yes. So it's interesting that there is a 0 down here, right? Is there? Do you have an explanation why this is? Yes.
This
So, the first time I talked about my collaborating car maker, so the target is a medium size. They want to solve this size, but I asked them to give us a bigger one because I want to check the scalability of ASP. So that's all. Anything. And the big one is somehow created by adding the vehicle type and equipment to the medium one. So, and I'm not sure what. I remember there is no special reason for the dependency constraint. The number of dependency constraint is 0, but this is just the instance from the car maker.
I understand. Thank you very much. Yeah, it seems because intuitively you would say the more options you have, the more could be in conflict with each other, right? Okay. Any further question, maybe? Well, if not, then thank you again. Thank you very much.
Thank you.